All right, sorry about that. My dog was, well, he was doing what my dog likes to do, which is bark at cats and squirrels. All right, ready? So let's go ahead and let me pick up where I left off. So I've already mentioned that the following bases are what we would consider the natural basis for R2 and R3. And you'll have to forgive me because I cannot remember if I've already read Theorem 7 to you or not, but I am going to read it again, and I want to talk about one more quick space. So the unique representation theorem basically says, look, if you have a set of vectors and it is a basis for a vector space, then you should then, or you could think of it as, then for each vector in that vector space, there has to exist a unique set of scalars such that you can reach any vector in that vector space by a linear combination. Long story short, we already know that the points 1, 0, 0, 1, that we can plot any point that we want in all of R2. But if I come along and give you a new basis, yes, the graph paper might look different, but if it truly is a basis of R2, then I also should be able to reach any point in R2 space with those new base vectors. So, all right. Now, one thing that we have not discussed a whole lot is polynomial vector spaces or polynomial spaces. And let me start by, let's just think about something here. It's very easy when I say R2 is all the points of R2. It's very easy to visualize that. But let's take this quadratic equation. Right, so this is so ax squared plus bx plus c. So will you agree with me, assuming a is not 0, that depending on the value of a, b, and c, there is a whole lot of different graphs that could be graphed, and just by choosing different values for a, b, and c, right? Well, the whole collection, meaning every single one of those graphs in would represent the polynomial space, right? The polynomial vector space of degree 2. That would be just like R2, the vector space R2 is all the points in R2. The vector space the polynomial, the p sub 2, would represent all the graphs that you possibly could reach in this quadratic equation. So now what I want to do is talk about, just like I talked about the natural basis of, say, R2 or R3, let me talk about the natural basis of a polynomial space. So when your polynomial is of degree 2, then, and I'm going to erase the 1, I'm going to erase this for just a second. What I'm going to write is a 1 here. What you're looking at, this set, is the basis for a polynomial space. So don't you see how the t squared and the x squared and the t is the x and the 1. Now, again, you can think about that as having 1 times c, or t to the power of 0. That's what I started off with. T to the power of 0 is 1. But this is how you would think about the natural basis for that polynomial space of degree 2. Now, the question that we still have not addressed is, okay, if I come along and give you a basis, how do you show that indeed it is a basis for some vector space? And we're gonna do one with a polynomial space, so you should take some good notes here. So I'm going to read the question, but this S is a set, and someone is claiming that set forms a basis for a vector space. Ready? But let's read. It says, show that S is a basis for the polynomial space of degree 2. Now, I just wrote on the previous page that the natural basis, right, for a polynomial space looks like this: a t squared plus b times t plus c. Which, what we're going to do is we're going to talk about what you must show in order to answer the question that S is a basis of the polynomial space. And what we're going to have to show is two things. Let's start with one. First thing we need to show is that S spans V. Now, I wrote equals here. I'm not being sloppy. But what I mean is that every graph that you can reach from this equation here, right? You should also be able to reach all the same graphs using a new basis for the polynomial space, right? So that's what I'm trying to say here, that V equals S, meaning all the graphs can be reached. Now, the second thing that we also have to show is that S, all right, this potential basis is linearly independent. And all that means, of course, again, is there is no multiples. All right, let's start with the first one. So that V is equal to S. Now, notice that I have V written on the left side of the equation, and you've seen me write that multiple times, so you're not going to be confused there. But wait a minute, what happened here, right? Well, remember that S gave you what the new basis, and they're claiming that this is a basis for all of the polynomial space. So, but with the new basis, instead of having a t squared, we had a t squared plus 1. Instead of having a t, we had a t minus 1. Instead of having a 1, we have 2t plus 2. Okay, so how is this going to work? Well, what I'm going to end up doing is I'm going to end up setting, so I've started by setting these two equations equal to each other. And what I'm going to do right now is I'm going to go ahead and distribute. Okay, so let me do that now. So this would be a sub 1 t squared plus a sub 1 plus a sub 2 times t minus a sub 2 plus a sub 3. I'm sorry, so plus a sub 3 times 2t and plus a sub 3 times 2. I'm going to write that as 2a sub 3. The very last ones I'm going to write as that as 2t a sub 3 plus 2a sub 3. All right, and now the only thing I want to make sure I did not make any silly mistakes, I think I'm okay, but let me just double check. All right. So now, what I'm gonna do is let's see if you can follow me here. So I'm gonna collect like terms. So anything with a t sub t squared I'm gonna collect them, group them together, and anything that has a t attached is gonna get grouped together. And then anything with no t at all is going to get grouped together. Ready? So let's go ahead and group everything up. So a sub 1 t squared, there were no more there were no more t squareds. All right, and then plus, I'm going to do two things at once, and I don't let me show you. This is not bad. So let's you and I agree that the following terms, these two terms, are the only terms that have a t. So what I'm going to do is you can think of it as I group them beside each other, and then I'm going to factor out a t. Okay? So that's what's about to happen right now. So if I factor out a t, I would be left with a sub 2 plus 2a sub 3. So and there's my t that I factored out. All right, and now I'm going to do the same thing here, except but there's nothing to factor out, obviously, because there's no t attached. But I'm going to take anything that's left. So, and let's see, was there anything else? And the a sub 3. Okay, so there's no t attached here either. Ready? Let's go ahead and finish this up. So this would be a sub 1 minus a sub 2, and then finally plus 2a sub 3. Okay, so perfect. So there's no t variables in here. There's t to the power of 1 here, and there's t squared here. All right, now at this stage, what I'm going to do is grab v, bring it down, and let me go ahead and show you what's about to happen here. So I'll clean this up just a little bit. So plus c equals. So now you can think of it as almost like you're setting coefficients equal to each other. Okay? So in this case, let's start with the very first coefficient. So we have a sub 1 attached to t squared on the right side, and what do we have attached to t squared on the left side? Well, just a. So my first equation in this little system that we're going to build is what? Well, it is I'm going to write it as a sub 1. I'm going to write the way that you're used to forming a matrix, is equal to a. Okay? This is an a. Not a very good-looking a, but it is an a. Is equal to a. All right. And that's even worse. Okay. Ready? And now, let's take whatever is attached as a coefficient to t. So I have a b. And then let me take whatever is attached as a coefficient to t over here, and I'm going to set them equal. So let's go ahead and do that. So that would be a sub 2 plus 2a sub 3 is equal to b. And last, I think you already see, I'm just going to take c and set it equal to a sub 1 minus a sub 2 plus 2a sub 3, and that is equal to c. All right. Now, let me finally show you what this new basis looks like, right? So let's get a view of what S looks like. So this is a system of equations, right? We have 3 equations, 3 variables, and you're welcome to go into a matrix at this point if you want to, but I think it's much easier just to see it as, since a sub 1 is equal to a, that makes life very easy. What would a sub 2 be equal to? Well, a sub 2, that's very simple. A sub 2 is going to be equal to, and you can think about it as doing row operations if you'd like to think of it that way. Let me Let me actually see if I've done a little bit of that work on the next page. So hold on. Ready? Yeah. So once I've gotten my system, it's perfectly fine to go ahead and place it into a matrix if you want to work out these row operations. But the idea is a sub 1 is very simple. A is equal to a sub 1. So let me go ahead and write that again. So a sub 1 is just equal to a. Now, let's figure out what a sub 2 would be equal to. Ready? Well, the row operation that I'm doing is negative 1 multiplied by row sub 3 plus row sub 2. Right, so take a look at, this is row sub 3. So if I do negative 1 times row sub 3 plus row sub 2, then what we end up with is the following. So we end up with A plus B minus C over 2. All right, so here is how we define A sub 2. All right, finally, A sub 3. Again, you can go back into your system and use some row operations, but I think this is things that we've been doing since chapter 1, so I don't think I think you'll be able to follow me fairly easily here. This would be C plus B minus A divided by 4. Okay. All right, so what is happening here? How do we figure out, so how does this work? Or more importantly, maybe what have we done? So let's assume that you know, or let's do this. Let's do this. So here's an example just to point out what we just did. So I'm going to write some, first let me write the regular degree 2 polynomial. But more importantly, what we're going to do right now is I'm going to make up an A, make up a B, make up a C. Ready? So let's assume for just a second that A is equal to 2, B is equal to 6, C is equal to 13. So let's plug in for A, B, and C. So that would be 2t squared plus 6t plus 13. Now, do you agree with me that this is just one of an infinite amount of graphs that I could have graphed from this equation, right? You with me there? You could go into your calculator and graph this right now. But I want to know, with this new basis, what should I have put here for A? What should I have put here for B and C with the new basis? Well, as you can see from up here, if you were to, let's start with the easy one. So since A sub 1 is equal to A, then if you have a 2 in the position of A, then you would have a 2 in position of A1, A sub 1. So we know that A sub 1 is equal to 2. What about A sub 2? Right, because this is a brand new basis. So, well, let's go, we would plug in 2 for A, 6 for B, 13 for C. Right, so we plug these in. What would come back out would be negative 5 halves. Now, same thing for A sub 3. We would take the A, plug it in, the B, the C, plug it in, and we would figure out what A sub 3 is. And we can do a little bit of arithmetic and figure out that A sub 3 is equal to 17/4. Now, here it is. If you've dozed off, if you just come back to me right now, here it is. So how do we graph, right? Because this is this is a graph that we could do in our calculator right now. And the question that we're trying to answer is how do we arrive at that exact same graph using this new basis? Well, very simple. You're just going to plug in 2 and -5/2 and 17/4. Ready? It would look like this. So 2 times, now what do we have in the place with the new basis where we used to have a t squared? Well, now it would be t squared plus 1 minus 5/2 t minus 1 plus 17/4 2t plus 2. And what I'm telling you is if you graph this in the new basis, you would get the exact same graph that you would have got from here. And this is true, right? This would be true for all A, B, and C. In other words, we have answered question 1 that for sure S does span V. All right. Now, the second part of this question, right, is how do we show that it is linearly independent? And we'll take a break after this, but remember to be linearly independent. Ready? Let me write something here. So if I'm down here, C sub 1 times V sub 1 plus C sub 2 times V sub 2, if I have a homogeneous equation, it's set equal to 0. And remember, to be linearly independent means they're not multiples of each other. So the only way to get to 0 is by choosing weights of 0, right? Recall? It should only work for the trivial solution. And that's what I must show right now. All right, and how do we do that? Well, notice that what I'm doing is I'm back to that same system. Now I've placed it into a matrix, but see, this time, instead of having A, B, and C, I know that A, B, and C is equal to 0. This is a homogeneous system. We know it's equal to 0. So in this case, we can just RREF, and what you would find is that you have a system that only works. It only works. I don't have, my apologies, I don't have a calculator in front of me to run a reduction algorithm, but not that we couldn't do it by hand. It wouldn't take very much time, but the idea is what you would find is this would be true, right? This here would be true only for the trivial solution. That tells us we have met both qualifications to be able to make the statement that the following is a basis for this polynomial space. Now, I understand this is a little bit trickier to do polynomial spaces than it is to do vector spaces like in R2 and R3, but this is very good practice. I hope that you took some good notes. But what you must show is the same. You must show both of these in order to make a statement about a basis. I will see you again in a little bit.